So as I said, introduction to quantum mechanics is nothing but the failures of classical mechanics. There are so many phenomena that were not defined or that cannot be explained by classical mechanics. Okay, so classical theories, so we need some other theory so that we can justify our experimental result. One or two such examples were photoelectric effect and Compton effect. And what happens in photoelectric effect and Compton effect, we will just see now. uh, Here a particle can be classified as a free particle and a bound particle. Now any particle, we can write the energy of the particle as energy is equal to kinetic energy plus the potential energy, right? Kinetic energy, we can write it as half mv square, the energy due to motion, and potential energy due to position, that is v of r. So total energy is nothing but kinetic energy plus the potential energy. Now if the particle is free, it means that it is not bound to any potential, not bound to any potential or force. It is not bound to any potential or force, which means v of r is equal to 0, and so energy is nothing but half mv square. Half mv square, or in terms of a momentum, we can write p square divided by 2m. And here we can write this v can have any values. So starting from 0 to infinity, any value is possible. That means for free particle you have continuous energies. Continuous energy. Why? Because velocity can have all values of velocity. From 0 to infinity, any value it can have. So similarly, this p square or v square value is also from 0 to infinity. Thus energy is positive. This energy is positive from 0 to infinity, any energy, so it is continuous. There is no gap. Now in the case of bound particle, which means the particle is bound to some potential, v of r is not equal to 0 here. The potential is not equal to 0. The good example is electron is bound to a nucleus. It is bound to a nucleus, v of r. This electron is under a potential v of r. So energy, we can write total energy is equal to p square divided by 2m plus v of r. Let us take this example. If it is in hydrogen atom, we can write the total energy is equal to p square divided by 2m minus z e square divided by 4 pi epsilon naught r. Now this z you can remove because we are talking about hydrogen atom. So e square divided by 4 pi epsilon naught r. So for hydrogen atom, this value is also equal to 1 by 2 into e square divided by 4 pi epsilon naught r minus e square divided by 4 pi epsilon naught r. Together we get 1 by 8 pi epsilon naught r into e square, or e square divided by 8 pi epsilon naught r with a minus sign. This minus sign indicate this electron is bound to the nucleus. This electron is bound to nucleus. This negative sign, total energy is negative. Total energy is negative means if you want to make that electron free, you have to give energy. If you can give energy, you can make that electron free until and unless it will be bound to the nucleus. Now here this R cannot have all values. You know Bohr model of atom. R is quantized. Because R cannot have all values. Similarly, because of this reason, this total energy cannot have all values. So this energy is, since it cannot have all values, it is called quantized. So energy of a bound particle is always quantized, while that of a free particle is continuous energy. Now, for a free particle, we have seen the energy is continuous, and for a bound particle, the energy is discrete. Now let us see, here you have 1D box. Our aim is to find at what time or when does this free particle energy become discrete. Okay, here you have a 1D box. 1D box means inside the box your potential V of R equal to 0 and wave function psi is not equal to 0. Wave function psi not equal to 0 means if there is a particle inside, wave function not equal to 0 means the particle inside, there is a particle inside it. The wave function not equal to 0 means there is a particle inside this box, and at this limit, extreme end, that is at if you write this x equal to 0 and x equal to L, the length of the box, at x equal to 0 and x equal to L, your potential V of R is equal to infinity. V of R equal to infinity. Which, why? Because we do not want this electron or the particle inside the box to go out of this box. If it has to go out of this box, it should have infinite potential. We should give infinite potential to this electron or this particle inside the box so that it escapes the box. Alright. Now this is about 1D box. And this free particle, the wave function psi is given by under root 2 by L. This is a constant. Sine n pi x divided by L. N pi x divided by L. And this n pi by L, n pi divided by L is called k. So you can write this as under root 2 by L sine kx. So what is this energy? Energy is equal to kinetic energy plus potential energy. But potential energy is, this potential energy is equal to 0. So what is kinetic energy? P square divided by 2m. P square divided by 2m. Now from de Broglie's wave, we have P is equal to h divided by lambda, or lambda equal to h by p. So h by lambda, just multiply and divide by 2 pi. So 2 pi h divided by 2 pi lambda. This h divided by 2 pi is nothing but h cross. H divided by 2 pi is nothing but h cross. 2 pi by lambda. 2 pi by lambda is nothing but k, wave number. These both are same thing. K and this k, both are same thing. So h cross k is equal to p. Another dimension or another formula for finding out momentum. P is equal to h cross k. Now just substitute the value of this p equal to h cross k here. So that is equal to h cross square k square divided by 2m. Now what is this k? Here you have what is k in terms of this length of the box. So we once again we can write n square pi square by L square, that is k square, h cross square by 2m. So that is equal to n square pi square h cross square by 2m L square. This you can write it as n square into, here pi is a constant, h cross is a constant, 2m and L is a constant. All are constant. So you can write it as E. So your total energy, or you can write E naught. So your total energy E is equal to n square E. Total energy means energy of the nth state. Nth state. The electron, if it is in the nth state, your energy is given by this. So when energy is for first n equal to 1, for n equal to 1, E1 is equal to E naught. For n equal to 2, E2 is equal to 4 E naught. N equal to 3, 9 E naught. So now this becomes a discrete energy. So when the particle is inside a box, a free particle inside a box is considered as this particle is having discrete energy n square E. So based on the previous slides that we have discussed, you can classify a particle as free particle and a bound particle. Now we also understood that a free particle, when it comes to a lower size box, you can, or this behaves as a bound particle. So there is a small change in the definition of free particle. The free particle, a particle without the potential is a free particle, is no more true. It doesn't justify. So how to give the clarity? A free particle or a particle is defined as free or bound. It depends on the availability, the space available for motion. Space available for motion of the particle. To make this clear, I will just give you an example. You assume that there is a room. The room dimension may be 3 meter by 4 meter, and you are placing an electron in the room. The electron, the dimension or the radius of this electron is around 10 to the power minus 18 meter. So 10 to the power 18 meter, and this dimension of the box, or the room, so 3 meter by 4 meter. So it is never comparable with this electron, size of the electron. So now in this case, even though there is gravity, everything, external force, this is considered as free particle. Now let me give you another example. There is an electron, the size 10 to the power minus 18, and you are confining this to another box with 10 to the power minus 16 or 17 or 18 by 10 to the power minus 16. This becomes a bound particle. So this question can be there in your interview board also. If you say, just say a free particle is without potential, then it won't impress the interviewers. Interview board will not be impressed by that question answer. What you have to say? It depends on the size or the space available for the motion of the particle. So it means you have understood something out of your MSc syllabus. So space available for motion determines whether the particle is free or bound. If the space available for the motion of the particle is comparable to the size of the particle, then this is a bound particle. If it is not, that is a free. Anyway, this particle size will be always smaller than the space available for motion, assuming you can't put an electron in a 10 to the power minus 20 by 10 to the power minus 20 room box. Must be always greater than that. Okay. Now, this entire world or universe is made up of either it is matter or it is radiation. Anything you take, either it comes under, it will come under either matter or radiation. Now, coming to this radiation, we can say through some principle the radiation is considered to be wave, and through some other theory it is said as particle. That means the radiation is both wave and particle nature. Now some of the theories that states radiation is wave are our Huygens wave theory. Then you have Young's double slit experiment. Then phenomena like interference, diffraction, etc. comes under this radiation as wave. Now, same things, that is radiation is also behaving as particle. Few theories are given by Newton's corpuscular model. Then we have photoelectric effect, Compton effect. Then our theories regarding reflection, refraction, all comes under the idea that radiation behaves as particles. If radiation is having both particle nature as well as wave nature, similarly this matter also must have particle nature. Matter is as such, it is a particle, so it definitely should have a particle nature. Similarly, the matter should also behave as wave. This wave is called matter wave. Now, who has given this idea of matter wave? He is nothing but de Broglie. De Broglie's wave. That means if a particle is with mass m is moving at velocity v, then the wave associated with this matter is having a wavelength which is equal to h by p, where this h is Planck's constant, p is the momentum. And this is called, the wave is called matter wave. And the velocity at which this m moves is called
VMW, that is velocity of the matter wave. It doesn't have any physical significance, no physical significance. This matter wave doesn't have any physical significance. A matter wave, velocity of the matter wave, velocity of the matter wave given by VMW, which is equal to lambda times frequency, because you know velocity of a wave in a particular medium is equal to the lambda times the frequency. It will give you the velocity. Now we already know we have two equations. E is equal to mc square, that is for matter, and similarly E equal to h nu for radiation. And what is matter wave velocity is equal to lambda times nu, and we have another formula, lambda is equal to h by p. Just substitute these values. So lambda is equal to h by p, nu is given by E by h, E by h. Now what is E? E equal to mc square. So h by p mc square divided by h. And what is this p? P is nothing but mv. So we can write it as h and h get cancelled. mc square divided by mv. Momentum is mv. So that is equal to c square divided by v. Now what do you mean by this c square divided by v? If v equal to c, then velocity of the matter wave equal to c. But we always know this idea that v is always less than c. V cannot be or less than or equal to c. The maximum velocity it can have is c. So if v is always less than c, this particular value c square divided by v is always greater than c. C square divided by v is always greater than c. This is the reason why this matter wave is having no physical significance. Now here what you see is a constructive interference formed by matter wave. So you know, if a matter is moving, mass m, particle of mass m is moving with some velocity v, corresponding to that you have lambda is equal to h by p, and you also have vmw, that is velocity of the matter wave. Okay, now so as this mass moves with velocity v, it will produce waves. These waves at some point it will constructively interfere, and at some point it will destructively interfere. Now this is where it starts constructively interfering. Okay, now the maximum interference where it constructively interfere maximum is at this particular point, is where you actually see the particle. That means the probability of finding the particle at this particular point is maximum probability. Now at this point, minimum probability, that is 0. That means at this point it is not constructively interfering, it is destructively interfering. Now here the idea what I wanted to convey to you is, if you throw a particle of mass m, let's just you throw a ball, it will follow a trajectory parabola. So how you know that this is following a trajectory or parabola? Because at each point, you know, at each point you can actually see the particle motion, right? Now what do you mean by actually see? All at these points, when it reaches at these points, you are actually seeing the particle, which means it is constructively interfering at all these points when it reaches these points. Okay, and now as and when I decrease the size of the particle, now this mass m size I am decreasing to a microscopic level, quantum particle, then if I throw the particle, the trajectory I can draw is something like this, because actually I don't know where the particle is. I can just tell at this particular point I can find the particle with some probability. I cannot say exactly at this particular point the particle exists. I can say within this region there is some probability of finding the particle. So this is what exactly is quantum mechanics talking about. Quantum mechanics is all about probability of this particle. Finding this particle is this much. Probability of the energy, probability of the momentum, probability of the energy, probability of the position. So this is what is saying. Now what is this called? This is called wave packet. Wave packet. Now the velocity at which this wave packet moves is called group velocity. Group velocity is also called Vg. So group velocity, it is also called velocity of the matter, because this velocity of the matter is nothing but group velocity. At this point it moves. So at all the points, at what velocity this wave packet moves, at that velocity only this particle also will move. So that is nothing but v, velocity of the particle. Okay, now this is also called, this group velocity is also called rate of transfer of energy. Group velocity is indication of the transfer of energy, how fast the energy is transferring. At high speed the energy transfer is high. Now once again, through this figure, the probability of finding the a particle at this particular point where constructive interference takes place is called, is having maximum probability. Minimum probability at the ends, that means where destructive interference will take place. Throughout this wave packet, the probability will be distributed with maximum here and minimum at the ends. So probability of finding the particle will be maximum at the middle of the interference, and it decreases along the both sides. It need not be always in this way. At different waves, or at different wave, for different wave function it will be different. But here in this case, the probability is finding the particle is maximum at this point where constructive interference takes place. Here we have a stretched string, and we are producing a wave in this stretched string by allowing it to vibrate. The length is from 0 to L, and once we start vibrating it, it will form wave. So from 0 to L, you know the wave, it is half of the wave. So L is equal to half of the wave, that is lambda by 2, right? Now this is the node, and these two ends are antinodes. So it is having number of nodes equal to number of nodes, n equal to 1. So since n equal to 1, this is called fundamental overtone. Now to find out the wavelength produced by a fundamental overtone, you know the formula is lambda is equal to 2 times L divided by n, where n is the number of nodes. Here n equal to 1, so lambda is equal to 2L. Lambda is equal to 2 times L. Now the waves produced here is standing waves. Standing wave. You know the difference between standing wave and traveling wave. The main difference is in standing waves, they do not transfer energy. Do not transfer energy. They transfer energy. Traveling waves will travel once it travels with a Vg. How traveling wave will transfer energy by Vg, group velocity. That is what we know. So please keep this in mind, because we will be requiring it the later stage. Now if n equal to 2, we know lambda is equal to 2L divided by n, which is equal to 2L divided by 2, that is equal to length. So the wavelength lambda is equal to L. For n equal to 2 means this is first overtone. From 0 to L, the length doesn't change, only the frequency changes. For changing the frequency or changing the wavelength, we have to add a strain or stretch the wire. Now that is it. Similarly, for second overtone means n equal to 3. So the lambda produced, the wavelength produced is 2L divided by 3. So for if there are n number of nodes, so n number of nodes, the wavelength produced lambda will be equal to 2L divided by n. Now for a one-dimensional box, the particle in one-dimensional box, wave function is given by psi is equal to a sine kx, where k is equal to n pi by l. And from de Broglie we know lambda is equal to h by p, but we few things we know. P is equal to h cross k. Substituting that value here, lambda is equal to h divided by h cross k, that is equal to 2 pi into h cross divided by h cross k. And what is k equal to? N pi by l. So that is equal to 2 pi h cross divided by h cross into n pi divided by l. So pi gets cancelled, h cross and h cross. So what you get, lambda is equal to 2L divided by n. This is the very same wavelength that we have found out from extended string. So extended string, we know this is length 0 to L. This is node n equal to 1. So for that n equal to 1, we have lambda is equal to 2L. Now same here for n equal to 1. Here what is the meaning of n? N is state. Nth state. Nth state. Higher energy. Nth state wave function. So where this is the length of the box. Length of the 1D box. So if n equal to 2, lambda is equal to L. So this is what you mean by or what we have going to we have proved 2L by n, lambda is equal to 2L by n, which means we are finding similarities between classical and quantum. So for n equal to 1, that is ground state. For n equal to 1 ground state, this is called n equal to 1 is called ground state of a 1D box. Ground state of a 1D box, lambda is equal to 2L. For first excited state means n equal to 2. First excited state. After n equal to 1, ground state n equal to 1 exists. So lambda will be equal to L. And for second excited state means it is n equal to 3. So 2L divided by 3. A free particle of mass m is confined to a region of length L. So this length is L, 0 to L, a free particle. Free particle means potential is 0. So find the energy of the particle. So energy of the particle is nothing but kinetic energy plus potential energy. Kinetic energy we have to find, potential energy is equal to 0. So total kinetic energy equal to what? So kinetic energy means p square divided by 2 times m. So you need to find out what is p square. So it is enough to find lambda. If you find lambda, we can get p momentum. So this is lambda by 2. This is again lambda by 2. This is again lambda by 2. So 3 times lambda by 2 is equal to length L. Right. So lambda is equal to 2L divided by 3. Now what is P? P is equal to H by lambda. H by lambda. So what is P is equal to H divided by, what is lambda? 2L divided by 3. That is 3H divided by 2L. So P square divided by 2M. This is what we want, energy. So that's equal to P square means 9H square divided by 4 times L square. L square into 2m. So that is equal to 9H square divided by 8mL square. So this is the energy of this particle. If this is the wave formed by the particle. So this is the total energy. De Broglie wavelength of a relativistic particle. Now before understanding this de Broglie wavelength for relativistic particle, we will understand what is relativistic particle first. If there is a particle moving with some velocity v, either can be considered as a relativistic particle or a non-relativistic particle. Now, how to divide that relativistic and non-relativistic particle? If the kinetic energy of the particle is greater than its rest mass energy E naught. If the kinetic energy is greater than the rest mass energy of that particle, then this is termed as a relativistic particle. Suppose if the kinetic energy is less than the rest mass energy, then this is non-relativistic. Then, for example, if we consider an electron, kinetic energy of this electron must be greater than m naught c square, where m naught is the rest mass of the electron, which is equal to 9.1 into 10 to the power minus 31 kilogram. Now, as and when this electron start moving, the mass will start increasing by a factor of gamma times. What is gamma? Gamma is equal to 1 by under root 1 minus v square by c square, which is greater than 1. So, as the particle starts moving, its mass will start increasing. So that is why its kinetic energy will increase with respect as it goes increasing further to the velocity near to c. Its kinetic energy will start increasing. Then the rest mass energy. Rest mass energy is a constant for a particle. Now we can write total energy E, or E square is equal to P square C square plus E naught square. That we can write it as P square C square plus M naught square C to the power 4. So E square is equal to this much. So we can write E is equal to under root P square C square plus E naught squared. Or from this equation we can write, from the above equation we can write E squared or P square C square is equal to E squared minus E naught square, or PC is equal to under root E square minus E naught square. So what is de Broglie wavelength lambda? We can write it as H by P or HC by PC. So what is HC? Both are constant. HC divided by what is PC now? PC is equal to E square minus E naught square. So this is the de Broglie wavelength for a relativistic particle. De Broglie wavelength for relativistic particle. HC divided by under root E square minus E naught square, where E is the energy, total energy of the particle, and E naught is the rest mass energy of the particle. Now for a relativistic particle, we know lambda relativistic, lambda is given by Hc divided by under root E square minus E naught square. Now we can write that total energy E is equal to kinetic energy plus the rest mass energy, that is E naught. This is what is total energy. Now then the square of the total energy, we can write E square is equal to K square plus 2k E naught plus E naught squared. Right. Now what you want here? We want E square minus E naught square. So E square minus E naught square. So what is that? E square minus E naught square equal to K square plus 2k E naught, where K is the kinetic energy and E naught is the rest mass. Just substitute this value over here. So we get lambda relativistic is equal to hc divided by under root k square plus 2k e naught. Now as a special case we can write the non-relativistic. What is non-relativistic case? When kinetic energy is very much less than the rest mass energy. Okay, so kinetic energy is very much less than the rest mass energy. So here what we can do is you can write lambda is equal to hc divided by under root, take this 2k e naught common, so 2k e naught into 1 plus k divided by 2 times e naught. Now this k divided by 2 times e naught is a very small quantity, less than 1. So you can write lambda is equal to lambda, here you can write non-relativistic. So lambda non-relativistic is equal to hc divided by under root 2k e naught. And what is e naught? E naught is equal to m naught c square. So that's equal to hc divided by under root 2k m naught c square. So this c square with an under root becomes c. So what you get is h divided by under root 2 m naught k. So this is lambda non-relativistic. For a non-relativistic particle, the lambda non-relativistic is given by h divided by under root 2 m naught k. Now for a suppose this particle is free, another special case we will do. Again, suppose this particle is free particle. Free particle means we have energy is equal to kinetic energy, because potential energy for a free particle is equal to 0. So kinetic energy is nothing but the total energy of the particle. In that case, our lambda for non-relativistic free particle is equal to h divided by under root 2 m naught e. Now for a bound particle means what is kinetic energy? Kinetic energy for a bound particle is nothing but total energy minus V. For a bound particle, kinetic energy is equal to total energy E minus V. So just substitute here in this first equation. So lambda non-relativistic bound particle is equal to h divided by under root 2 m naught into E minus V. This is for bound particle, this is for free particle. So here you can say for a free particle for a free particle, if the lambda is lambda free and this is lambda bound, the wavelength of a bound particle increases as and when the particle moves to a area of a high potential area. So for example, you have a free particle here. This free particle is moving into some potential. Here the wavelength will be lambda free. Here the wavelength will be lambda bound. Inside this potential, your wavelength will increase. That can be one of your question. The de Broglie wavelength for non-relativistic free particle. So we have the formula lambda is equal to h divided by under root 2 m naught e. Now for a charged particle with charge q producing a potential V, then E is equal to QV. The potential times the charge is equal to its electric energy. So for a charged particle, we can write lambda is equal to h divided by under root 2 m naught QV for charged particle. Now suppose this charged particle is an electron. So what is the charge of this electron? Charge of this electron is 1.6 into 10 to the power minus 19 coulomb, and mass of this electron is 9.1 into 10 to the power minus 31 kilogram. Now substitute these two values. What you arrive at is lambda is equal to 12.26 divided by root V, where V is the potential. This much Armstrong. This is in terms of Armstrong. Or you can simply write under root 150 by V Armstrong. Root of 150 by V Armstrong. Now suppose this charged particle, instead of electron, this is proton. Then what is the change? For proton, there is no change in electric charge, but the mass changes, right? So when you put the values of mass of the proton, you get lambda equal to 0.286 divided by root V. This is also in Armstrong. Now suppose instead of this proton, you have an alpha particle. What is the change? Let us see. For an alpha particle, lambda will be equal to under root 1 by 0.101 by root V Armstrong. So what are the things to remember? The lambda for a de Broglie wavelength is given by this formula. For a charged particle, E is equal to QV. So lambda equal to QV. This is the general formula. And from this we have taken, if the charged particle is an electron, then we get lambda electron. So this is the for electron, or this equation. Now if the charged particle is a proton, then your wavelength is this one, lambda p. And if the charged particle is an alpha particle, your equation is 0.101 divided by root V Armstrong. Now we have lambda for a relativistic particle, that is free particle. Relativistic free particle is equal to h divided by under root 2 m naught e. Now for a neutral particle kinetic energy is given by 3 by 2 k by t, where 3 is the number of degrees of freedom. If it is moving in 3 dimensions, this is for 3D motion. So it is 3 by 2 kbt. That means 3 times half kbt. Now, so for neutral particle, this much. So for lambda relativistic, for free particle, for a neutral particle will be equal to h divided by under root 2m naught into e. E is 3 by 2 kbt. So that is equal to h divided by under root 3 m naught kbt. Now let us see for neutral gas particles. For neutral gas particle, we consider total kinetic energy is equal to kbt. Well, what is kb? Kb is Boltzmann constant. Kb is Boltzmann constant. So for neutral particle, lambda will be equal to h divided by under root neutral gas 2 m naught kbt. Here there is a free particle with kinetic energy k. So here you have k, and de Broglie wavelength lambda enters into a region of potential V. So here you have lambda, here you have lambda dash. They are asking what is the de Broglie wavelength in the region. So that is lambda dash in terms of k, lambda and V. Now what is the total energy here? Energy here is equal to k, and what is the energy here? That is equal to k plus V, kinetic energy plus the potential. Right. Now here what we can write here, lambda is equal to h divided by under root 2 m naught e. Now lambda dash is equal to h divided by under root 2 m naught into e minus v, m naught into e minus v. Now bring this lambda dash or this e outside. So this will be h divided by the root 2 m naught e minus v. What is e minus v? So e into 1 minus v divided by e. Right. And what is this particular quantity? H divided by 2 m naught e. That is the lambda. So that we can write it as lambda dash equal to lambda divided by under root 1 minus v by e. Now what is this? E is equal to, or we can write it as lambda divided by under root e minus v by e. E minus v by e. That's equal to lambda divided by, what is e minus v? K, under root k divided by k plus v. Again we can simplify. lambda into under root, this will become numerator. So k plus v divided by k, that is 1 plus v by k, 1 plus v divided by k. So this is lambda dash. Now in terms of total energy, we can write it as lambda dash equal to lambda divided by under root 1 minus v by e, and in terms of v and k, lambda dash equal to lambda into under root v by k. Consider a charged particle at rest which is accelerated by an electric field E. So let us consider here you have a charge source that which is being with an electric field E. So this charged particle Q will be under the influence of this electric field. So corresponding force will be equal to F is equal to E times Q. Right. Now what is the question? Find the rate of change of de Broglie wavelength with time. Now as and when this particle, this is at rest right now. So when there is an electric field applied, this charged particle Q will be moving towards it or away, depending on the charge of the particle. Now let us assume it is moving in towards. Now as and when it moves towards this electric field E, its velocity increases because force increases, right? There is an acceleration. So what is acceleration? Acceleration will be equal to force divided by mass of the particle, which is nothing but eq by m. Now when velocity increases, momentum will increase. When momentum increases, the de Broglie wavelength decreases. So lambda, here it will have some lambda. When as it moves, lambda changes. Now what is the v equal to? V equal to u plus at. Now what is u? U initially the charge is at rest, so it is not moving. So velocity will be a times t. What is a? A is nothing but eq divided by m into t. But we know lambda is equal to h by p, that is equal to h divided by m v. So that's equal to h divided by m into what is v? eqt divided by m. So m and m get cancelled, so that is equal to h divided by eqt. So that is equal to lambda. So as and when t increases, lambda decreases. But this is not the question. The question is what is the rate of change of de Broglie wavelength with respect to time. So d lambda divided by dt. This is the question. Lambda with respect to time. What is the rate of change of lambda with respect to time? Now here we can write h is h, e and q is there. So h divided by eq. The derivative of 1 by t is nothing but minus 1 divided by t square. So that is equal to minus h divided by eq t squared. So this is equal to d lambda by dt. So this is what is the required answer. Now the question is whether it is moving away from the electric field, away or towards. That means if it is positive and negative charge, what will be the change? There is no change. The ratio will be same. Ratio of d lambda by dt towards positive side and negative side will be same because force is same. Find the relation between de Broglie wavelength and Compton wavelength of a relativistic particle. The relativistic particle wavelength is given by lambda is equal to hc divided by under root e square minus e naught square. But what we know is E is equal to gamma times E naught, where E is equal to mc square and that is equal to gamma times m naught c square. So m is nothing but gamma times m naught. Now substituting the value of E, so we get this is equal to hc divided by under root gamma square E naught square minus E naught square. So that's equal to hc by E naught into 1 divided by under root gamma squared minus 1. So that is nothing but hc divided by m naught c square into 1 divided by under root gamma square minus 1. So under root gamma square minus 1. So c and c get cancelled. What is h by m naught c? This h by m naught c is nothing but our lambda c, which is Compton wavelength. Lambda c divided by under root gamma square minus 1. Now what is gamma square minus 1? Gamma square minus 1 is equal to 1 divided by 1 minus v square divided by c square minus 1. That's equal to 1 minus v 1 minus of 1 minus v square divided by c square divided by 1 minus v square divided by c square. So 1 minus 1, so that is 0, minus of minus plus, so that is equal to v square divided by c square divided by 1 minus v square divided by c square. So this is gamma square minus 1. So under root, so what is under root gamma square minus 1? Or let us write down 1 divided by gamma square minus 1. So what is 1 divided by gamma square minus 1? That will be equal to 1 minus v square by c square divided by v square by c square. So that is equal to the c's, this will become, just separate it. So this will become c square divided by v square minus 1. So this is 1 divided by gamma square minus 1. So what will be 1 divided by under root gamma square minus 1? That will be equal to under root c square by v square minus 1. So this is 1 divided by gamma square minus 1. Now we have lambda. This is equal to lambda, right? Lambda de. So lambda de is equal to lambda c divided by, instead of gamma square minus 1 we can write into c square divided by v square minus 1. So once again we will write lambda de is equal to lambda c into under root c square divided by v square minus 1, or you can write lambda de divided by lambda c is equal to under root c square by v square minus 1. Find the velocity of a particle whose de Broglie wavelength is nothing but the Compton wavelength. So de Broglie wavelength is equal to Compton wavelength. So in that case, what is the velocity of the particle? So we know, we have a formula lambda de is equal to lambda c divided by under root gamma square minus 1. So this is the relation between de Broglie wavelength and Compton wavelength. Now for these two quantity to be equal, that means if lambda de equal to lambda c, then this denominator, what is in this denominator must be equal to 1, which means under root gamma square minus 1 should be equal to 1. This is implies gamma square minus 1 equal to 1, which means gamma square equal to 2. So what does that mean? Gamma is equal to root 2. Now what is gamma? Gamma is nothing but 1 by under root 1 minus v square divided by c square is equal to root 2. Again, you can take gamma square. So which means 1 divided by 1 minus v square divided by c square equal to 2. So 1 is equal to 2 into 2 minus 2 times v square divided by c square. So this becomes half. Bring this to the side. So v square divided by c square is equal to half. V square divided by c square equal to half. So which means v is equal to c divided by root 2. C by root 2 means 0.707 c. So this is the speed of that particle where its Compton wavelength will be equal to the de Broglie wavelength. Here we are going to find out, or we are going to learn how to find out the velocity when gamma is given. When gamma is given, how will you find out the velocity? Now in the previous question we have gamma is equal to root 2. Now what you have to do is you have to write this gamma in a as a sides of a right angled triangle. So we have a right angled triangle here. So write it as a fraction, gamma equal to root 2 divided by 1. Okay, so now this gamma, the numerator is hypotenuse and the denominator is any other side. Let me call it as side 1. So I am writing this root 2 here as hypotenuse and side 1 as 1. Now what is the velocity? How will you find out velocity? Velocity is nothing but side 2, that is another side, divided by hypotenuse into c, where c is the speed of light. But what is the side 2? Side 2 will be 1, right? This is side 1, this is side 2. What is side 2? Side 2 is 1, because you know was s1 square plus s2 square is nothing but hypotenuse square. So side 2 is 1. What is hypotenuse? Root 2 into c. This is the speed of light that you got in the previous example. So that is v equal to 1 by root 2c. Another example is, let us take gamma is equal to 5 by 3. We know 4, 5, 3 and or 3, 4, 5 are Pythagorean triplet. So 5 is the hypotenuse, 3 is one of the side, another side will be equal to 4, right? So 4 times 4 by hypotenuse into c, this is equal to v. So this is the speed of the light when gamma equal to 5 by 3. Another example you can take, gamma is equal to 13 divided by 5. Again we know 5, 12 and 13 is a Pythagorean triplet. So what is the another side left? That is 12. If you want you can write it here itself. So this is 13, this is 5, this should be 12. So what is speed of the particle? V is equal to 12 divided by, that is another side divided by 13 into c. So this is the speed of light. Sorry, speed of the particle away which is moving. So that the gamma is equal to 13 by 5. So usual method, it will take at least 2 to 3 minutes to solve. First you have to square, then rearranging the terms, But here there is nothing to square and do um, difficult steps. Only simple trick to remember. Just remember how you are following. That would be enough. To find gamma when velocity is given, that also we will use the same formula, same technique. So velocity is given, so velocity, let us take it as 3 by 5. 3 by 5 times the speed of light. Okay, so how we can go? So here when you write v is equal to 3 by 5, take this as side 1 and 5 as hypotenuse. So hypotenuse goes to 5, side 1 goes to 3. Now what is the left side? uh, that is 4. Now gamma is given by hypotenuse, or you write hypotenuse divided by side 2. That is nothing but, what is hypotenuse? 5. What is side? 4. So that is gamma is equal to 5 by 4. Gamma equal to 5 by 4. Again you can write velocity is equal to 0.8 c. 0.8 c. Then you can write it as, it is equal to 8 divided by 10 c. So hypotenuse is 10, 8 is the other side. What will be the side 2? So this is 10, 8 and 6, which is again another triplet. 6 square 36, 8 square 64, that is equal to 10 square 100. So what is gamma equal to? Gamma is equal to 10 divided by 6. That is nothing but 5 by 3. 5 by 3, that is gamma. So this is how you can find out. Sometimes in the question you will be asked to find out, you will be requiring v, that is speed of the particle, or sometimes you may require gamma. For example, a particle moving with 0.8 c, a particle of mass m naught is moving with a velocity equal to 0.8 c. What is the mass of the particle? At a rest mass, rest mass is m naught, and this particle is moving with v equal to 0.8 c. Then what is the mass? So what is the mass? You have to, mass is nothing but gamma times m naught. How will you find out gamma? Through this method. So gamma is equal to 5 by 3, right? So it will be 5 by 3 times m naught. This will be the mass of the particle right now when it moving with 0.8 c. Now here is a question. Find the de Broglie wavelength of an electron in a hydrogen atom. Now here is the center, this is the radius. We don't know what is the position of the electron, whether it is in first excited state or a ground state or any other state. Let us, for example, let us take it as nth state. Nth state. So this would be Rn, the radius of the nth orbit. Right. Now we know angular momentum L is nothing but mvr, r cross p, angular momentum. So from here we need mvr, that is, so that is quantized mvr, angular momentum, quantization of angular momentum, which is nothing but nh cross, or you can write it as nh divided by 2 pi. So this is angular momentum quantization. So L is equal to nh divided by 2 pi. So mv is equal to nh divided by 2 pi r. Now what is this mv? This is nothing but momentum p. Now once you know momentum, we can find out lambda. What is lambda? That is equal to h by p. So that is equal to h divided by nh into 2 pi r, right? So 2 pi r. So this is nothing but 2 pi r. We can write subscript n divided by capital N. Here also you can write rn just to indicate it is in the nth state or nth orbit. So lambda is given by 2 pi rn divided by n. So for n equal to 1, that means it is in the ground state, 2 pi r1. This r1 is nothing but you write it as a0, the ground state radius of a hydrogen atom. 0.5 angstrom. So when n equal to 2, you write 2 pi r2 divided by 2, where r2 is the radius of the second orbit. So this goes on. So this is when r is equal to 1. When n equal to 1, you get 2 pi r. That is circumference of the orbit. Here it is half the circumference. This is first orbit. It's half the circumference of second orbit, not the first orbit. It changes. It doesn't mean the wavelength equal to half the first time. No, it means for the second orbit, its wavelength will be half of the circumference in the second orbit. So when n equal to 3, 2 pi r3 divided by 3. So this is how it goes, and that is the de Broglie wavelength of electron in that hydrogen atom. So for n equal to 1, I think we have already seen how the waves this will be like this. For n equal to 2, this will be the shape of the wave. For n equal to 3, this much.